Okay, so let's speak about recursion. So what is a recursion? Recursion is essentially a reduction of a problem into itself, right? Now, this sounds silly. This sounds like a snake eating its own tail, which is not a good idea if you're a snake. So don't do that. But the important thing here is that we reduce the problem into instances of itself, maybe one or more instances. But the important critical thing is that those instances are smaller. So we are making progress. And this is very similar conceptually to inductive proof. So in reality, reduction and induction are two faces of the same coin, right? One is algorithmically, the other is mathematical, proof technique. But in reality, they're the same thing, right? You can think about induction as just a recursive algorithm for proving correctness. That's all it is. Of course, the natural question is to see example of such a reduction, because it ultimately doesn't seem very natural, but in fact, it turns out to be extremely common, because in a lot of problems, it's kind of easy to reduce the problem into something smaller, but this something smaller turns out to be an instance of the same problem. So, and of course, you get this recursive algorithm that reduces the problem into smaller instances until you reach the bottom, where you reach really small instances, and then you solve them using brute force. Now, when you think about recursion, the way I like to think about it is that think about having, you want to solve a problem of instance of size n, whatever n is, and somehow magically give you a black box that can solve a smaller instance, like n minus 1 or n over 2, right? Let's say n over 1, n minus 1. Right? It can solve instances that are smaller. And the question now becomes, okay, how can I solve my problem of instance n with this box? Think about it as a different box, B, that can solve smaller instances, right? So in fact, when you think about it as a black box, then okay, I give you a black box that can solve a smaller instance, then you can build an algorithm to solve the original instance. So you get an algorithm that, think about, you get an algorithm A to solve an instance of size n using a black box B that solves smaller instances, right? And here's the big striptease. You say, B is not B, it's really A, right? But conceptually, it doesn't matter, right? The fact that B is really A, right? So conceptually, when you want to think about it, it really is more convenient to just think about reducing A into smaller instances, and the smaller instances are somehow solved magically by a black box B, and the fact that B is in fact A doesn't enter the issue, right? And so that's the way I like to think about it. It's also a very important thing when you design recursion is not to open the black boxes, right? So the most destructive thing you can do when you think about recursion is that you start opening the boxes. Or you say, we do this in A, and then we reduce it to a small instance, and then those smaller instances called the other instances, and you start opening the boxes, and the structure mentally becomes very complicated because things get very complicated, and you lose track of what's happening. So when you think about recursion, it's really important to keep the black boxes closed. Those are Pandora boxes. Don't open them, and then things become very clean conceptually, which is always nice. And it's somewhat counterintuitive to think in this way. This is why recursion is usually difficult to people to master, but it's one of those techniques that if you master, you really kind of you master kind of the main tool or one of the main tools in designing algorithms efficiently. Okay. So let me give you one of the classical examples of a recursive algorithm. You must have heard of it before. This is the Towers of Hanoi. So the story goes that monks, there is some temple in Hanoi, that there are those discs. I think there are 64 discs or whatever the number is. And those discs were initially ordered as a tower like that. And the task is that you have to move all the discs from one tower to another tower, from this side to this side. And that's it. Now, of course, this is a very easy problem. You just pick all the disks and you move them. So we're going to enforce some bizarre rules. So first, we're allowed to move only one disk at a time. And secondly, those disks are very brittle. So you cannot put a bigger disk on a smaller disk. You're required to move, put smaller disk on bigger disks, right? So it does have to look like that. And you have only 3 pegs, right? In fact, it's an interesting problem to ask what happens if I increase the number of pegs, right? It's not hard to show that, for example, if I allow you n pegs, you can do it in a linear number of moves. A move, again, is to move one disk to one peg to another, complying with the size constraints. So if you have n or n plus 1 pegs, you can just essentially lay out all the pegs, and then you just collect them back into the destination peg. So this is easy. But here we have only 3 pegs. So that makes things nasty. And the algorithm is, of course, very easy. It says, okay, forget for a second about the bottom disks. Okay, take the tower of n minus 1 of them and remove them into the middle peg. So that we can do, right? That's easy. And how do we do that? Well, this is moving n minus 1 disk. We definitely can do it because recursion, right? If it's a single disk, we know how to do it. Otherwise, as I said, recursion. So we get to this configuration. Now this disk on the left side is now a single disk, so we can move it directly to the peg on the right. And now finally we take those n minus 1 disks and we move it to the right here. No. And again, this movement of this tower of n minus 1 disk to here is done recursively. Now, all you have to convince yourself is that if you do this algorithm, you're always going to make legal moves. But it's in fact easy to see because this largest disk always remains on the bottom, right? It's bottom doing this step, starting a move, and it's the bottom in this stage, and it's the bottom in here stage. So it's always in the bottom, which means that indeed it's legal, right? So that's nice. It's a legal algorithm. Of course, the question is how many moves do we make? Here's the pseudocode for this, which I'm sure you've seen earlier in your academic career, and you get this recurrence, right? Moving a tower of n disk require two times moving disk of size n minus 1 plus 1. Okay. Now, of course, we're interested in the value of Tn, right? So there are 2 ways to do it. One of them is to just guess the solution and then verify, right? So I'm going to guess that this is 2n minus 1. Why did I guess this? Well, because it just works out. So let's verify that this is indeed the solution. So t of 1 is, of course, 2 to the 1 minus 1, which is 1. So this is true. And t to the n is just 2 to the tn minus 1 plus 1, which is 2 times 2 to the n minus 1 times 2 plus 1, which is magically enough 2 to the n minus 1. Right? So I verified the solution. Right? So this is, frankly, this is the main technique of solving recurrences. You guess a solution and you verify it. But you don't have to guess. In fact, all the recurrences you will see in this course, you can solve them. They are not that difficult. So how would you solve these recurrences? Well, here's one way of solving this recurrence. This is not the only way. But you can just do repeated application, right? So you take tn minus 1, you write tn as this, which is the definition. Now you take tn minus 1 and you open it, right? You write down what it means, right? So you write it down and you expand, right? So this is 2 to the 2 of tn minus 2 plus 1 plus 1, which is equal to what's written here. Right? And then you repeat doing it, right? Now, if you're repeatedly doing it, what you're going to get, you have to prove it by induction or convince yourself, you're going to get an expression of the following form. 2 to the n minus 1 t1 plus 2 to the n minus 2, and so on all the way to 1, right? And this is a sum of powers of 2, and sum of powers of 2, consecutive power of 2, and this is as such equal to this. The easiest way to see why this is true is just to think about it in base 2, by the way, because this is in base 2, this is just 1, 1, 1, 1, 1, which is of course just 1, 0, 0, 0, 0, 0, 0, 0, minus 1, which is exactly this. Okay, so that's the number of operations this recursive algorithm performs, and it's not hard to convince oneself that you cannot do better than that. And that's it for now.